Hi, I'm very short content and this is my Physics 2211 Lab 1 report. So the purpose of the lab was to analyze the motion of an object moving in a constant velocity, to track and graph the motion of the object using a tracking software, to make a computational model representing the predicted position and comparing it to the actual observed position, and to understand the concept of Newton's second law and how no net force means the object moves at a constant velocity, as well as understanding the update position and velocity formulas. So these two formulas are shown on the right. The update position formula states that the final position is equal to the initial position plus velocity times delta t, and the velocity update formula states that the final velocity is equal to the initial velocity plus the net force over the mass times delta t. So the principles of this lab that are explored are Newton's second law. We aren't taking friction and air resistance into account, but Newton's second law is essentially force is equal to mass times acceleration. Equilibrium, which basically states that when the net force is zero, the object is either at rest or constant velocity, and the principle of constant velocity, which means that there is no acceleration. So Newton's second law and assumptions. Newton's second law is force is equal to mass times acceleration. The net force equals, of course, mass times acceleration, but it can also be written as net force is equal to mass times change in velocity over change in time. We're assuming that there's no air resistance or friction force for the computational model, although it will be there in the real life model. The system is the car and the surroundings are everything else. So as you can see on the right here, these are Newton's second law equations, but they just come in different forms, but they all essentially convey the same idea. So potential errors, there could be a data difference in the models due to friction. We didn't take into account friction for the computational model, so that's why the models are different. And there could be a data difference during the tracking process. Of course, there's human error when tracking the cart and potential software errors as well. So this is the software we use to track the cart. As you can see, we have a video with red dots that are marking the cart as it passes through each stage of its path. And this tracking software subsequently created this graph, which shows a linear upward trend because the object is moving to the right at a constant velocity. And this graph is a position time graph where x is in time, so seconds, and then the y is the meters, or the distance in meters. So we had to write code. So the code was written in Python using GlowScript. It shows how the graph is going to look and what data points it will use. The inputs were the initial velocity and the initial position. The initial velocity had a vector of 0.597, 0, 0, which was determined by using the average velocity between 2 points. And the initial position had a vector of 0.3909, 0, 0. So the computer model code, it shows Newton's second law, force is equal to mass times acceleration. It uses the position update formula and the velocity update formula. The net force was set to zero because the object is moving at a constant velocity. And this net force vector was 0, 0, 0, of course, because there was constant velocity, meaning there was no acceleration. So the experimental model is in red and the experimental model is in blue and the computational model is in red. As you can see, the computational model overestimates the distance traveled. This is because the computational model does not take into account friction and tracker calibration. And this explains why there is an overcompensation in the distance that was recorded. So some follow-up questions. What if the axes were flipped? The graph would have a negative slope and the velocity would also be negative. However, it's still constant and the net force is still zero. The model will still overpredict because friction and air resistance are not taken into account. What does it mean? It means the net force is still zero because the cart slowed down. This is because of outside forces like friction and air resistance. It'll be still difficult to say all the forces acting on the object. However, there are definitely some forces acting on the car. These include gravity, drag, and friction, but of course, it's tough to say all the forces that are acting on the object. All the conclusions will still essentially be the same for the lab. The computational model will still continue to overpredict. It's just that if the axes were flipped, the graph would have a negative slope.